Okay, welcome my dear students. Come on to this new session. In the last session, we discussed about the show that the important theorem. We can say that if we have T is a linear transformation from V to W, then there exists another linear transformation S from W to V, and we can say that this is 2 is T is invertible if such that Ts is equal to identity and St is equal to iso identity. Okay, in this class today we have to discuss some important composition rules. What about? So we start with a theorem. Let V and W be U, V and W be vector spaces. U is V to W, U to V, S is this linear transformation. So we just say that it's clearly linear transformation. We just take T from you have a U to V, and then we have a V to W, we have a S. Now we have a this is a, you have a composition. So composition map we have to define as T is a component composition map is equal to you have a U to W. Then we see what about if S and T are isomorphism, then you can say that St is also isomorphism. Then means we clearly say that there is two parts of this theorem. One is if S and T are both the isomorphism, then we have to show that St is an isomorphism, and St inverse is equal to we have a T inverse and S inverse. Another part of this question is saying that if St is 1 1, then prove that T is 1 1. And another part we have to just say that this is means we can say that St is a 1 1, then we have to prove that T is also is a 1 1. If St is on 2, then we can say that S is on 2. So now you see what we saying that whenever S composition is a 1 1, then this T is 1 1, then composition is on 2, then this S is on 2. And now again we can say that if St is an isomorphism, then T is 1 1 and on 2. That is clearly because St is isomorphism means we can say that St is a 1 1 and on 2. If St is a 1 1, then we can say that T is 1 1. If St is a on 2, then we can say that T is on 2. That this is a proof is by combining these two results. We can easily get the proof of this last one. Now the last one is if we have a U, V and W all are the same finite dimensional, then St is isomorphism, then both S and T are isomorphism. So this means we have to just say that here we have to just say that T is 1 1 and on 2, but here what we say that V, U and W are the same finite dimensional vector spaces, and also we have a given St is an isomorphism. Then we try to prove that both S and T is also isomorphism. Okay, so we can prove this theorem is by one by one. So I just first we try to prove that the first one is S and T are isomorphism, then St is isomorphism, and St is equal to this is inverse of is equal to is this form. So now we have a giving S and T is isomorphism. So S and so this means S is you have a 1 1 and on 2, and T is also you have a 1 1 and on 2. Okay, so we try to show that St is also, so composition is 1 1 and on 2. So we just try to show that first is a this composition is 1 1. That means if one of the method is this, we can take any element of a this kernel of a St, and then we show that this kernel of St, because T from you have a U to V, and we have a so we have to just say that U to V, we have a this is you have a T, and then we have a V to W, we have a S. So we have a composition map. St is you have a U to W. So we take some element U belongs to the kernel of St. Then we try to show that this implies that we show that this U is nothing but is equal to 0. If we success to prove that this U is equal to 0 is true, then we can say that this kernel of St is equal to 0, and then St is an 1 1. Okay, so we just take since S is an isomorphism, so we just take a S inverse is defined, and then this condition by the previous theorem, we can say that is isomorphism, the S inverse exists, S inverse is equal to identity of a W, and S inverse S is also is equal to identity of a V, because it is isomorphism, though since S and T both isomorphism, similarly T is isomorphism, so we can say that also we can say that T into T inverse is equal to identity of a V, and T inverse T is equal to identity of a U. We have to using these two conditions, so we just try to show that ST is an isomorphism. So either we have to show that this S T inverse is equal to this way or way. So we can just compute isomorphism ST is equal to this. So one of the method we can say that ST and we can say that S of a T and then we have a T inverse S inverse is equal to identity, or we have to show that T inverse S of T is equal to identity. If we succeed to prove this, then we clearly say that this is equal to true into this form. Okay, so now we just say that ST S of T can be written in this form. So by S and T all are the linear transformation. Inverse is also linear transformation. This can be written in the form of a S of a this. This can be written as a S of T inverse over S inverse. Now T inverse is equal to, we have to just say that T inverse is equal to identity of a V. So we can say that S of identity of a V into S inverse. This is nothing but is equal to, we can say that S of S inverse, then we can say that identity of a W. So we can just say that this is identity of a W. On the other hand, we just try to this way compute this. So we just write in the form of a T inverse. We just take a S inverse S of a T. This can be written as a T inverse S inverse S T. Now T inverse S, and then we have a T. Now you know that we have a T inverse S inverse T inverse T is equal to identity U, S inverse S is equal to identity of a V. So we just take into this is S inverse is equal to identity. So T inverse we have a identity of a T, then we can say that T inverse T, and this can be say that identity of a V. So this means we show that we have to show that ST or T inverse S inverse is equal to identity, and then also show that T inverse S inverse ST is also identity. Then by the this implies that we can say that ST ka inverse is equal to, you have a T inverse and S inverse, inverses exist, and then we have to just prove this. And then by the previous result, ST from this is an isomorphism at its inverse given by this. So this means we can say that if we have to show that ST is an invertible matrix there exists, then this S is an ST is an isomorphism, and its inverse is given by this. ST is equal to, you can show that this is equal to this thing. Okay, so now this complete the part of this second. I just leave this S and T are isomorphism. The ST is an isomorphism. By you have as a home assignment, you can just say that ST of a U can be written as a S times of a T of U, and then because S and T are isomorphism, and we can just say that this can be written as a by the automorphism. We can say this is nothing but is equal to T of U. This is S is 1 1. So this means S is 1 1 means S of T of U is equal to U V. We can show that. So this means you can just try yourself by this is isomorphism. Next, if S isomorphism and ST is isomorphism, you take a ST of we can take a U. This can be S times of a T of U, and T of U is equal to 0. Why? Because T is a 1 1. So T is 1 1 means U is the element of a kernel of this means S of 0 is equal to 0. So we can say that S of t is equal to 0 of 0 of u, v identity of a v. So we can say that also 0 maps, so 0 to t u is equal to 0. If u is equal to 0 means we can say that ST is a 1 1, and similarly we can prove that as for a. So this is a home assignment for you. You can try. If S and T are isomorphism, then ST is also an isomorphism. Okay, now we just prove the second part of this theorem. The second part of this theorem is saying that you have to we have a B part of this theorem. This one we have to try to show that this one, the B is a ST is a 1 1, then T is a 1 1. So ST is a 1 1, then we try to show that T is a 1 1. So take a this is a NT, I mean say that kernel of a T. U is the element of a kernel of a T, then T of U is equal to 0 of a V. Okay, now this is equal to 0 of a V, then T of ST of a U can be written as S times T of a U. Then T of U is equal to 0. So we can say that U is 0 and S of 0 is equal to 0. So STU is equal to 0. Since ST is a 1 1, so it follows that ST is a 1 1 means we can say that this is equal to, we have a STU is equal to, this means U is equal to, we have a 0 of U. Then hence kernel of a T is nothing but is equal to, you have a this 0 subspace, then T is equal to 1 1. So if ST is a 1 1, so if ST is a 1 1, then we can say that if STU is equal to 0 implies that U is equal to 0 of U, and then we can say that this is 0 only the case when 0. So this is true, and then we can say that clearly kernel of a T is equal to 0 subspace. If kernel of a T is equal to 0 subspace, we can say that T is a 1 1. Now next we show that ST is onto, then S is onto. So we show that ontoness, then we take any element W belongs to the W, and now since ST is a onto, so we have just said that S and T we have just take the form of this U to V and V to W. This is T, this is S, this is your ST. ST is the element of a U to W. So if W belongs to W, then ST, there exists some U belongs to U, STU is equal to W. So by the ontoness of this, we can say that clearly ST of U is equal to W. Because ST is a onto, so ST is onto means there exists some vector U. This satisfies this condition. And now by the definition of a composition, STU is equal to W. Now if there exists a vector V belongs to T of U, because you have to, that is T from, you have a U to V. If U is the element of a U, there exists some element, this is T of a V. So V is nothing but some element of V can be written in the form of T of a U form. So V can be written in the T of U is the element of a V. So if the element of a V, we can say that S of V is equal to, you have a W. So ultimately what is this is a V, so S of V is equal to W, and S is a map from, you have a V to W, then there exists a V, and we show that S of V is equal to W, and W is the element of a W. We show that S of V can be written in the form of a W, then S is onto. So if we have a ST is onto, then we have to prove that if ST is onto, then S is onto. So this means we prove this this is the C part of this theorem. Also now we try to form the last part. D part is a first show that T is 1 1. So first we show that T is 1 1. So L this is kernel of T, and T is a kernel of T, the same thing. If U belongs to the kernel of a T, then we can say that T of U is equal to 0. And then S composition T of U is equal to 0, and then we can say that S of ST of U is equal to 0 of W. This implies that we can say that U is the U is the element of a kernel of a ST. So this we can say that an ST is an isomorphism. So T is 1 1. So ST is is equal to isomorphism. This implies that this ST is 1 1. So, ST is a 1 1 means you have a u is equal to 0. So, ultimately u is equal to 0. This means this is kernel of T is equal to 0 and this T is a 1 1. So, now we show that T is 1 1. Now, we show that ST is onto, then S is onto. So, W is the element of a W, ST is a onto. There exists a U belongs to U such that ST U is equal to W. Then S composition, by the definition of a composition, this can be written as S times T of U is equal to W, and then we can say that there exists some V can be written in the form of a T. V is the element of a V. S of V is equal to, you have a W. So, this implies that S is an onto map. Okay, so, now this complete the proof of the third part, D part also. Now, we move to the last part of this theorem. In the last part of this theorem is saying that you have to prove that if ST is an isomorphism, then it is a both 1 1 and onto. And then by the part D, we know that T is 1 1 and S is onto. And the statement is saying that a dimension of U is equal to dimension of a V is equal to dimension of a W. Means is saying that clearly the dimension of all the vector space are the same. And now, we know that the result, if we have a T from U to V is a linear transformation, and if T from U to V is a linear transformation, and dimension of U is the same as a dimension of a V, then we can prove that if T is if T is 1 1, if and only if T is onto, then we can say that T is onto. So, clearly by this result in the dimension theorem, we have to prove that where we have a, if U T from U to V and dimension of a U and dimension of a V are the same. So, we can say that if T is 1 1, if and only if T is also onto. Okay, so, now because ST is an isomorphism, we have a given. In the previous result part, we show that if ST is isomorphism means ST is 1 1 and also ST is onto. If ST is a 1 1, this implies that by the part D, T is 1 1. And part D is also show that if ST is a onto, then we can say that this is a S is onto. So, if ST is an isomorphism, then we can say that T is 1 1 and S is onto, but the dimension of this T and W are the same. By this theorem, we can say that if T is 1 1, this implies that T is onto, and also by the same theorem, we can say that if S is onto implies that S is 1 1. So, we can show that S is T is 1 1 and T is onto. This implies that T is an isomorphism. S is 1 1, S is onto also. Then we can also say that from this by this result, we can easily show that this is T and if ST is an isomorphism, then S and T is both is isomorphism. Okay, so we just write list. T is 1 1 and dimension of a U, then T is onto. Therefore, T is isomorphism. Similarly, S is onto, dimension of this, again S is 1 1, this is S is an isomorphism. Okay, this way we can just complete the proof of this result. Is very trivially we can say that if we have all the properties of this theorem, I just go back and then explain you little bit. This theorem, we just prove all of them part is done. I just leave this this part. If S and T are the orthomorphism, then you prove that ST is an isomorphism. is your home assignment. You try yourself because you can just try by the using the ST's isomorphism, showing that isomorphism S and T is isomorphism. You use the some element of a kernel, U is the element of a kernel of ST, and then show that this U is nothing but is equal to 0 by using that S and T are isomorphism. So S of T of U is equal to, you have a 0. Now by the composition mass, T of U is equal to 0. Now because T of U is equal to this is S of T of U is equal to 0. Now S is a you have a 1 1, so S of 1 1 means T of U is equal to 0, and T is 1 1, then U is equal to 0. So we ultimately we get that U are element of a kernel of this ST. Then we show that U is equal to 0. This implies that we can say that kernel of ST is equal to 0 subspace. This implies that ST is 1 1. Now similar fashion you can prove that some element of a W belongs to the W, then you show that ST of V is equal to W. So some there exists some V belongs to the V such that S of T of V, S of T of V, and then T of V is nothing but T is on 2, so S and W sum, and at S is on 2, then this is equal to W. By this method you can try yourself for this problem. I already showed that this ST is a 1 1, and now okay, this completes the proof of this theorem. So now we I just try to discuss one small problem before closing this session. If we have a V is a one dimensional vector space and S and T are V to V a linear map, then prove that ST is equal to TS. Okay, so V is giving, we have a V is given, V is a one dimensional, so V be a one dimensional. Then that means dimension of a V is equal to 1. So this means there is a basis is only one element. Suppose V is a element and this V should be a non-zero. If it is 0, then clearly it is not a basis. So in the dimension of a because the dimension of a V we have a giving 1. If the dimension of a 1, then the basis is only element of a 1. So this element of a any element this is V. So any arbitrary element V belongs to V can be written as a finite linear combination of the element of the basis. So V can be written as alpha times of a or we can take some element U is the element of a V. U can be written as alpha times of a element of the basis. Okay, so by this element of a basis we can just say that S and TB are a linear map. So we can say that that S we just prove that ST is equal to TS. Okay, so we start V is a one dimensional vector space. So V be a basis for V, and then there exists a alpha and beta are the element of F such that T of V, because this is a linear map, this is the basis for V. So we can say that T of V can be written as a alpha V, and S of V can also written as a some beta V is there. So we can say that we can calculate S of T of a V, then S times we can say that T of a V, and this is nothing but is equal to, we can say that S times T of V is equal to, you have alpha V, and now ST is, this is a linear map, we can write alpha S times of a alpha of a V, and this implies that we can say that alpha times you have a S of a V, S of V is equal to beta, so alpha times of a you have a beta of a V, then we can say that alpha beta times of a V. So this means S of T, S composition T, V is equal to alpha beta V. So S composition T is equal to alpha beta V. Now we have to calculate the other part of this composition map, and the other part is we have to calculating the T of S over V. By the definition, this can be written as a T times of a S of V. Now T times of a S of V, we have a beta times V, and this is nothing but is equal to T times of a beta V, means this is T is a linear, so we can write a beta times, we can say that T of V, and beta times T of V is nothing but is equal to, we have a alpha times of a V is equal to beta alpha times of a V, and then we know that the alpha beta are the element of the field, and then alpha beta is equal to same as a beta alpha. So, this can be written as a, we can write alpha beta of a V, and now we already proved that alpha beta V is nothing but is equal to ST of a V. Now, this result is true for each and every V is the element of a vector space V. Then we can show that this is nothing but is equal to ST is equal to, we can say that this is equal to TS. So, this means we can say that this we complete the proof of this theorem. This property we can show that if we have a T from V to V1 to V1 कह सकते V1 to V1 means we have to just say that is a dimension of this vector space is equal to 1. So, if we successfully prove that, if we have a, in general we show that the composition of a two map ST is in general not equal to, we have a T of S is not equal to, we have a S of T. But if we take a one dimensional vector space V, then we have to show that if I have a V is a one dimensional vector space and T and ST are the two composition of a ST is the same as a TS by using this the method of this thing. Because it is one dimensional, we use the technique of a basis, and by the basis conditions we can also using this proof of this in the similar fashion. So, that means we can prove that this is clearly I already proved that this is a composition of a two linear transformation and need not be a transformation, and also we define a different type of a linear transformation where we can say that one of the S composition T is equal to 0, but T of S is not equal to 0. In the previous class I proved this means we have to find such a types of a linear transformation when composition of a ST is equal to 0, but composition of a T is not equal to 0. And we also discuss in the previous classes, that means composition of a linear transformation is associative, and also we just prove that this composition of transformation we can easily find the inverse of a transformation by using the invertible mechanism. We can take, there exists another linear transformation, we take a S with the this another transformation, for example T with the S is identity, then ST is also identity, then we can say that then T is the inverse of S, or vice versa, S is the inverse of a T. In this case we just successfully complete the this. So, I just stop today class at this point, and I have to stop here, but in the next class we try to discuss some properties of a composition of a linear map. Means we just try to what is the relationship of a rank and nullity of a composition of a linear transformation, and also we try to some finding the inverse, or finding the find the how to find the range, rank, nullity and kernel of the composition of a linear transformation. So, we discuss all these problems into the next class. So, in the next section we discuss some problem based on this composition of a linear transformation. Okay, thank you very much for this class.